Hello everyone. In today's lecture, I'm going to talk about waveform generation, input capture, PWM motor interfacing. This is going to be a comprehensive lecture as we are going to cover chapter 15, 14 and 16 accordingly. Because these are all related to each other, and in the end we are going to see how AVR is dealing with this all together. We have to go into the details of each chapter carefully. So let's give a start and see the outline of the lecture. We'll start with the waveform characteristics and we'll talk about generally how we can measure the frequency, the period, the amplitude or the duty cycle of a waveform. And then the waveform in AVR, what kind of resources we are using in AVR to generate a waveform. Then input capture, if you want to capture an input event, again which part of AVR is used, what resources are we using, and some examples will be given. Then we'll talk about the hardwares that we can interface with AVR, like the drivers, the relays and the Opto isolators. And we'll move on to the motor control, how we can use the motors. Then the PWM modes, so the fast and phase correct modes. Right, let's start with the wave characteristics. When we talk about a wave, we are talking about a train of pulses. And these train of pulses have their period and their duty cycle and their amplitude. Now let's go one by one and identify those. So the period is starting from maybe either the rising edge, till the next rising edge. This is a period of one cycle. So this is known as T. Now, if you want to find the frequency, we just need to do 1 over T. I believe you all know this. I'm just reviewing them. Now, when we talk about the duty cycle is, let's say we start from the one falling edge to the next falling edge. Again, actually we are covering a period over there. But the duty cycle is this low pulse and the high pulse width are important in duty cycle. And generally, we can say that the duty cycle is, let's say this is T0 and this is T1. We can say T1 over T times 100. And actually that T is T1 over T1 plus T2 times 100. This will give us the duty cycle of that wave. And another characteristic or a parameter that you would like to say is the amplitude of that wave. And that amplitude is all fixed for a wave that we are generating. Normally represented with small letter A. So I'm assuming that you know these from your previous courses. I'm not going to go into the details, but we are going to use the frequency, the duty cycle and the amplitudes wherever we required in interfacing or generating waveforms with AVR. Now, let's get into the AVR waveform generation. So in chapter 9, we have seen that for each timer there is at least an output compare register. For example, for timer 0 it's OCR 0. The value of this register is constantly compared with the TCNT register that we are counting in the timer. And when there's a match, the OCFN flag will be set to high. This is what we have seen in the timers chapter. Now, as you can see from the slide, in each AVR timer there's also waveform generators. These waveform generators can generate waves on the OC-N pin. OC0, OC1, OC3, OC2. We can use any of these pins to generate waves. The only thing that we need to take care, the control register of the timer, there was a mode selection bits, VGM-N and COM-N. So those mode selection bits has to be configured to determine how the register, the waveform generator is going to work. So we can either configure it to have it in the normal mode, or we can have it in a CTC mode. So for example, when TCNT N register reaches to the top or bottom, or maybe compare match occurs, the waveform generator is in form. Then the waveform generator changes the state of the OC-N pin according to the mode of the timer, which is decided by the VGM-N bits, TCCR register, and also the COM-N bits. Now, if you want to do with the timer 0 or timer 2, we have got an 8-bit comparator which compares constantly with the TCNT value, and we can use the OCRN values over there to compare it. And whenever there is a match, it sets the flag like we have done it in the timer section, and we can generate a waveform. So how do we generate a waveform? If you can see it over here, when there's a flag is generated, that flag is actually triggering the waveform generator. So we have got top, bottom, FOCN, force output compare, and the mode and the COM bits over here, which we are using in TCCR. Now, based on that, OCN output is going to be set. So OCN is an alternative function in one of those ports, as you can see, because we will have 7 of them. So you can find it on port B or port E or port B as well. And either you can configure it as a normal input-output pin, or you can configure it specially for output waveform generation. So if we configure the timer 0 in this case, we can control that by using the COM bits of the TCCR and send out a waveform. As you do remember the timer 02 configuration for an 8-bit timer, you can see the details of it over here, that we can use the CTC mode or the normal mode, and with the COM bits we can actually use the toggle compare match, or clear on compare match, or set on compare match. Now, with the non-PWM waveform generation modes, we also have again the pre-scaling modes for CS if you want to use. So what is happening over here? First one, the waveform shows actually the system clock, let's say 8 megahertz. Then the second one is showing the pre-scaled clock. Now the third graph shows the TCNT count, and it updates on the falling edge of the pre-scaled clock. On our first pre-scaler, we have the pulse out. The TCNT is top -1. So this is the first one. That was the start. That's the first one. So it's top -1, which is in this case 254 for 8-bit. Then on the second one, for the pre-scaler pulse, it reaches to the top, which is 255 FF. Now on the third pre-scale pulse, the TCNT register overflows back to the bottom, and which is 0. Now on the fourth pre-scaler, the TCNT register starts to increment from bottom +1, bottom +2, up to 255 again to the top. Now the fourth graph over here is showing that OCRN, it's specified with the top. So we don't need to compare anything. Whenever it overflows, it will generate and interrupt, or it will raise the flag and it says it's overflowed. So now we can generate a waveform. So these can be calculated with some formulas. I just want to go through over here. We have got 2 modes, which one CTC toggle output compare mode. So with the duty cycle 50% and frequency can be editable or changeable. Now in this case, we start from 0, we specify the OCR value that we want to compare. When the timer TCNT reaches that value, and when there's a compare match, it resets to 0. Now in every match over there, as you can see, our square wave is toggling. So on this edge, it's falling down because we started as rising at level 1, and it's going to fall down, and it will leave up until counting up to OCR value again, and then when it matches, it will generate another pulse on the waveform generation and carries on. Now the formula that we are using for FOCO0, the frequency of the system clock, we have got 2 times the prescaling factor and OCR0 plus 1, which is the output compare value that we use. And this will generate with a duty cycle with 50%, but we can change the frequency of the wave. Now in the second mode, we have got toggle OCO0 mode, but the duty cycle and the frequency is changeable over there. So we can specify different OCR values throughout the waves, and we can generate a different wave. So for example, for the OCR01, first it counts up to OCR01, then when it matches, it generates the first pulse, then it counts up for the second one, when it matches, it generates the second one, and third one. So as you can see, the pulse widths are changing with the OCR values. And again, we can use a similar formula where we have got the frequency of the clock, again the prescaling factor, the values of the OCRs plus 2, and the duty cycle is OCR0, 1 plus 1, and then OCR01, OCR02 plus 2 can be calculated. You don't need to memorize any of this, but you have to know how we are calculating the duty cycle or the frequency of the generated waveform. Now, to generate these square waves, I'm just repeating, we can set the timer to normal mode or CTC mode and set the COM bits to the toggle mode, which is 0, 1 in this case, and the OC0 pin will be toggled on each compare match and square wave will be generated. There's a small example over here. Assume the clock frequency is 8 MHz, generate a square wave with duty cycle 50% and frequency is 500 kHz. So everything is given for us. Now the F clock is 8 MHz, so the frequency of the wave is 500 kHz, and just need to put all the values over there. The only thing that we don't know is the prescaling factor and the OCR0 value. And once we rearrange the equation, we can write it as n OCRn plus 1 will be 8 over 1. So this is actually going to give us 8 at the end when we cancel out. Now, as we have got the prescaling factor and the output compare register value plus 1, what we can say about is we can just find out two values for n. Either n is going to be 1, then OCR is going to be 7, so 1 plus 7, 8 times 1, it's going to be 8, or n is going to be 8, OCR is going to be 0, so 0 plus 1 is 1, and 1 times 8, it's going to be 8. So we have two alternatives over here. Either the prescaling is 1 and the OCR value will be 7, or prescaling is going to be 8 and OCR is going to be 0. So that we can configure the OCR values for the timer and also the TCCR with the prescaling either 1 or prescaling 8, depending on the configuration that you would like to use. And we can have a waveform separation either in normal mode or in CTC mode. So let's do a couple of examples related to this so that it will be easier to understand. Right, let's do the first example. It says calculate the frequency of the wave generated by the following program. Now DDRB bit 4, which is the OC0 bit pin, is set to be an output. Now we have got an OCR value as 100, which is the match value, and the COM0100 bits are configured to be the output is toggling, and we have got the mode as a normal, and there's no prescaler. So we set the TCCR, the control register, and we load it and we start counting. Now the few things that we need to consider: our period for the timer, as we are using 8 MHz clock, this is going to be 1/8 MHz. So this will give us 0.125 microsecond period. Okay, let's note that down. We are going to draw two waveforms. The first one represents TCNT0. So this is the place where it's 0 hex FF or 8-bit timer. So I'm just going to draw the dots over there. Then we have got OCR 0 value, which in this case is 100. And let's draw the dotted lines for that as well. Now I'm going to draw another graph which shows the OC0 output. They're both over a time actually. And this is 0 and we have got level 1. So what we need to take care over here, as we already said, as we are doing this in normal mode, that means we are going to count up to 100, but as this is normal mode, we have to carry on to up to FF, and when it overflows, it will start again and count up again. So that means we can have the count and then carry on. So over here, that we reach to our OCR 0 value, we can put down an output because of the flag, and let's say we started from level 0. So when it reaches over there, that means our wave is going to toggle, so it will be 1. Then it reaches to hex FF, then overflows and starts again, reaches to FF and overflows and starts again and overflows. Now when in each cycle reaches to 100, we are actually going to generate or toggle the OC0 pin, and this is going to be the case on this part as well. So we go up, then we go down, stay down, and we go up again. Now, so how do we do the calculation? This is actually going to count from 0 to 256, right? 0 to FF. So we can say that each of these is going to be 256 times the period, which is 1/8 megahertz. And this is also going to be 256 times 1/8 megahertz. Because from 0 to FF there are 256 clocks between the two consecutive matches. That's why we can write that down. And the waveform that we have generated, that's the period of it, that's going to be 2 times 256 times 1/8 megahertz, which is the period. This will give us the period of that wave that we have generated. So we can say T wave is equals 2 times 256 times 0.125, which is equivalent to 64 microseconds. And to find the F wave, the frequency of that wave, we just need to do 1/T wave, which is going to give us 15.625 kilohertz. So this is how we can use the timer 0 in normal mode for waveform generation. And once again, in normal mode, when match occurs, the OC0 pin toggles, and the timer, it actually continues to count up until it reaches to the FF, to the top value, and then it overflows and starts again. This is the normal mode. We are going to do the CTC mode a little bit later. The square waves in CTC mode, they are better than the normal mode for generating the square waves, because the frequency of the wave can be easily adjusted using the OCR0 register. So how can we do that? Let's create another diagram. We have got one waveform, again with TCNT0. So our 0 hex FF is there. Let's have the dotted lines. And OCR 0 value is there. Let's have that one as dotted lines. And again, we draw a similar waveform for the OC0 pin. This is going to be 1, 0. So in this case, with the CTC mode, depending on the OCR value, if we reach that value in CTC, when there's a compare match, it goes down, match again, goes down, match again, goes down, match again, goes down, match again, and goes down. As we already said, we can adjust the OCR value and we can easily adjust the frequency of the wave. So based on these matches, our output pin is going to toggle. Again, let's start with 0. So on the first toggle, it will rise up, stays until the second toggle, it goes down, stays low, goes up on the third one, stays high, goes down, stays low, and goes up, and stays high, and it goes like that. So we can say that in CTC mode, when OCR0 has a lower value, the compare match occurs earlier, and the period of that generated wave is smaller, so we can have a higher frequency waves over. Let's do another example. So similar waveforms. This time I'm just going to set OCR somewhere here, so higher than the previous one. So that's FF, dotted values, and this is OCR, and we have got logic 1 and logic 0. Now this totally depends on my drawing, if it's going to be a wider or not. So we go higher, we go down, compare match, we go higher, we go down, compare match, higher, down, compare match, higher, down, compare match. As we are going higher for the OCR values, we will have a compare match occurs later on. So this will actually generate a wave with a period which is longer. So let's say 0 first, and then 1, and then stays 1, goes down, 0, 1, and 0. So as you can see, as we are extending the pulses with the OCR match, we'll have a lower frequency for that waves. And please note that when the compare match occurs, the timer value will be set to 0 and starts again. So that's why we are coming down and starting again, down and start again. So this is how square waves in CTC mode is generated. Now the second, or let's say in this case the fourth example, it says 8 MHz, calculate the frequency of the wave generated by the following program. Again, the OC0 pin is set to be an output, so it's going to toggle, and mode is CTC, and there's no prescaler, and the OCR value is 200. Now in this case, let's draw it once again. We have got the waveforms, so over a time, we have got the hex value, which is 0 hex FF. We have got the OCR0, which is 100, and we have got logic level 1 and 0, and so on. So if we want to generate the wave, we have to count up 200, and to go over down, we need one more clock, which is going to be 201 in this case, and count up again 200 and go down +1, 201, 200 and down +1, 200 and down +1. Now each of these is going to generate the wave for this OCR value. Now we start with 0 again, go high, we set it 1, then low, and 1 again, and then low. Now each of these is going to be 200 plus 1 times again 8 megahertz clock, which is going to be 1 over 8 megahertz. So I forgot to switch the screen. This is 200 OCR value which is given for us. We start from 0, go up to 200, then down. We need another 1 clock, so that's why we have 200 plus 1 times the frequency of the clock, and we generate the wave when we have got compare match. And in the end, this is going to give us period as 2 times 201 times 0.125 microsecond. So this will be 50 times 25, 50.25 microseconds, and frequency of the wave, it's going to be 1 over that, which is equivalent to 19.9 kilohertz. So this is how we can generate the waveform or find out the frequency of that waveform. If you have any questions related to this, please note it down and feel free to ask during the QA session. Now there is one more example. It says find the value of TCCR 0 if you want to program timer 0 as a CTC mode, square wave generator, and no prescaler. Now it's actually how we are going to configure the TCCR register. So if you want to configure it as a CTC mode square wave, so CTC mode, this is going to be 0, 1, and we want to be toggling, so that means comms are going to be 0, 1 as well. So that's 0, that's 0, that is 0, that is 1, and that is 1. So 0, 0, 0, 1, and then 1 for that one, and we don't have any prescaling, so that's going to be 0, 0, 0, 1. So that will be 0, 0, 0, 1. In the end, we'll have 0 for FOC, 0 for VGM 0, 0 for COM 0, 1, and 1 for COM 0, 0, 1 for VGM 0, 1, and the CS bits for the prescaling is going to be 0, 0, 1. So this is how we need to configure TCCR 0 register. Generating pulses in CTC mode. When we configure a timer in CTC mode and COM is in the toggle mode, the value of the OCRN represents how many clocks it counts before it toggles the pin. That's what we have seen in the example. Now by using this method, we can generate different pulses by loading different values into the OCRN register. And in order to load the value to the OCRN, we can use compare match interrupts as well. Whenever it matches, it fires an interrupt, and inside of that interrupt, we can specify what will be the next OCRN value and count up to there. When it reaches, generate an interrupt, the next OCR value, and carry on. So we can say that when compare match happens, the pin will be toggled and interrupt will be invoked. So by using an interrupt, we can define the duration of the OCN pin's current state, and by loading a proper value into the OCR0 register. So the last example will show how we can interpret that. This code is given for us. We have got initialized stack, so we are using timer 0 compare match interrupt service routine, which is the vector specified over there. Then we initialize again the OC0 as an output, Now the OCR value is given as 69 at the beginning. So over here I'm just going to take notes because this is important. So the first OCR value is OCR 0 is going to be 69. Then the timer is arranged to be in CTC mode, no prescale, and toggle on match, and start the timer. So what will happen? We need two waveforms, but I want to extend this a little bit more because I'll have more values over there. Now we have got 0 hex FF over there, and we have got 69. So that's our first value, and the counter started. So we have got 1 and 0. Now we start and we count up to 69. So that's the first value set by the main program that OCR is going to reach. And when it reaches over there, it will come down. But when it comes down, this is going to toggle the OC0 pin. Now, the thing is, this is the main program, and when it toggles the OC0 pin, it's actually generating an interrupt. And that interrupt will help us to divert into the interrupt service routine. Let's go back to the program and let's see what's going on over there. So with the interrupt service routine, it says decrement R29. So we don't have any, we are assuming that it's 0 now. It says if R29 is greater than or equal to 0, go to L1. Now it's not greater than or equal to L1. That means we have to go through this stage. So we have got a wave table. So we have got a lookup table that we need to find out the values and plot those values for it. Start with the wave table, which is loaded, and the first value is 24. We initialize R29 to be 3, so that means 3, 2, 1, 0. That's a counter for us, and we have to plot those values as a waveform. We initialize 3, we get the first Z value, which is 24, and attach it to R28. So R28 will be copied into OCR 0. So the next value that we are going to have is 24. 24 is somewhere here, and I'm drawing dotted lines. That means when I run the interrupt service routine after 69, my counter is going to count up to 24, and then it will go down. So that will generate another wave over there. Let's say we started from 0 again. That will go up, and that's 24. And after 24, we return back to the main, but we count it. So when we count it, it's going to jump to an interrupt service routine again. But this time R29 will be decremented to 2. We get the next value, which is 49, and that will be loaded into OCR. So next value is 49. We have to count from 0 to 49. And whenever we reach to 49, we toggle it. So that toggle will generate the next waveform on OC0. And also, this will actually generate a new interrupt. So we'll go back, and that will be 1 now. And we will get the second, third value, which is 39. So we have to plot that 39. That was 49 and now 39. I've got dotted lines. That means our timer is going to go up to 39 and then down, and this will carry on generating the wave. And we have got one more, because when it says another flag, this is actually going to go for the last value, which is 34, as this is going to be decremented to 0, and the last value is 34. So let's write down 34 as well. Now 34 somewhere here, and timer going to count up to 34, and then it will come down and we'll have a wave generated on the OC0 pin. And then, as this is going to be continuous, whenever it reaches the new interrupt, it will carry on. So this is actually repeated with the, after 69, it's going to repeat with the 39, 49, so based on the sequence given over here, 24, 49, 39, 34, and back again 24, 49, 39, 34, and so on. This is what is going to be generated with this program. So we can actually create, with the different OCR values, we can create different types of waveforms in CTC mode. So this is done for timer 0, but you can also configure timer 1, 2, and 3 and in a similar manner to generate a waveform or generate a pulse in normal mode or in CTC mode. All you just need to do is to configure the control registers, the VGM modes and the COM modes, and you need to find the appropriate value for the OCR to generate the frequency specified. And watch out for the interrupt service routine. The next thing that we are going to cover in this lecture is input capture. We can use input capture in many applications. For example, recording arrival time of an event, pulse width measurements, or the period measurements. And in Atmega 128, we can use either timer 1 or timer 3 to detect and measure the events happening outside of the chip. So when an event is detected, the TCNT value is loaded into ICR1 register and the ICF1 is set. So as you can see from the Atmega 128, we have got ICP1 and ICP3 pins that we can use. And we load the low byte first and then the high byte and so on. And ACIC pin, which is the select bit for the multiplexers, we can use to select the event source. For example, it can be the analog comparator mode or it can be the ICP pin. So we can capture the analog comparator or the ICP based on the ACIC pin. Upon the detection of an event, the TCNT value is loaded into the ICR1 register and the ICF1 flag is set. So in input capture for the timer 1 or timer 3, we are going to set those bits, which is ICNC1 and ICES1 registers, the bits. So ICNC1 is the input capture noise canceller. So each change is considered only if it persists for at least 4 successive system clocks, and it causes 4 clocks of delay from the event occurrence to the load of the ICR1 register. If you're going to use the noise canceller and it's enabled, that creates a 4 clocks of delay because it's waiting, it's checking for the 4 cycles if it is a noise or the valid data, and then it loads into the ICR1 register. And for the input capture edge select, when edge is detected, the TCNT is actually loaded into the ICRX register, and it also raises the ICFN flag in the timer interrupt flag register. So we can decide the falling edge or the rising edge of the input capture. And as we already said, for the ACIC bit, we can choose either the analog comparator or the ICP1 pin for external event measuring. Now, as we already said, for the input capture, we can use it to measure the duty cycle or the period. There are various steps to do that. For example, to measure the period, we have to initialize the TCCR1A and TCCR1B, and we have to initialize the ACSR to select the desired event source. Then we have to monitor the ICIF1 flag in the timer interrupt flag register to see if the edge has arrived, and upon the arrival of the edge, the TCNT1 is loaded into ICR1 register, and we save the ICR1 register, and we continue monitor the ICIF1 flag for the second edge. And when the second edge is arrived, we do the same thing. We load the TCNT1 is loaded into the ICR1 register, and then we save the ICR1 as the second edge of the waveform. And by subtracting the second edge value from the first edge value, we actually set the time for it. So we can decide for the period. So the first edge and then the second edge will show us the period of that time. Or we can use this as a measuring pulse width of the event. So if you want to measure the pulse width, we have to initialize again the TCCR1A and TCCR1B, and we have to select capturing on the rising edge. Okay, we are saying that one. Then we initialize the ACSR to select the desired event source. We have to monitor ICF1 flag in the timer interrupt flag register if the edge is arrived or not. So when the edge is arrived, TCNT1 value is loaded into ICR1 register automatically, and again we save the ICR1 and change the capturing edge to the falling edge. So we first get the rising edge, now we are going to get the falling edge. We monitor the ICF1 flag again, and whenever it's set, we save the ICR1 for the second edge. And what we do, we subtract the second edge value from the first edge value to get the time over there as well. So this is how we can use input capture. Now the frequency of a pulse is between 50 to 60 Hertz. Assume that the pulse is connected to ICP1, which is the pin 4, PD4. Write a program to measure its period and display it on port B. Use the prescaler value that give the result in a single byte. And the system clock is 8 MHz. So what we need to do is, as it's going to be an 8 MHz, we can use a prescaler of 124. You can do these calculations from the timers. I'm not going to do that now. So the prescaler 124 is actually going to give us 1 over 124, which is equivalent to 7812.5. And in this case, T is going to be 1 over 7812.5 Hertz, which is going to be 128 microseconds. Now, the frequency of 50 Hertz give us the period of 1 over 50, which is 20 millisecond. So the output is 20 millisecond divided by 128 microsecond, which will be 156. And the frequency of 60 Hertz, which is going to be 1 over 60, which is equivalent to 16.6 millisecond. So the output is going to be 16.6 millisecond divided by 128 microsecond, which is equivalent to 130. Now we have got values for 50 and 60 Hertz, and we have to write the program for it. Let's start with LDI R16 0 hex FF for port B to be an output port. So out DDR B R16. and out port D R16. Now we are setting port B to be an output port, and we are also setting the pin D6, pin D4 actually, to be an ICP1 pin. So then we do LDI R20 hex 00 out TCCR1A, the control register for timer 1. It's going to be R20 because that's going to be timer mode as normal. Then LDI R20 0 hex 45, where out TCCR1B, it's going to be R20. So this is going to be setting, it's going to be the rising edge prescaler, which is equals 124, no noise cancellation. Then we wait for ICIF, so in R21 FR, we have to check if ICIF is set. So SPRS R20 TIFR IC1, so skip. Next instruction, if ICF flag is set, or jump. If it's not set, we have to jump back to over here. So let's say this is L1, and then we get first low byte R16 ICRL1 and save it. We can say R16 will be equals ICR1L, which is first edge value. Then out, we have to do TIFR, we have to reset it. We have to expect for the second edge. ICF1 is equals 0, and expect for the second edge IFR SPRS R21 ICF1. So skip. Next instruction, if ICF1 flag is set, and if not, jump to L2. Let's say this is L2, and then get the value in R17 as ICI RC1L, and we can say that R17 will be equal to ICR1L, where the temp is ICR1H. This is our second edge value. We do out because we have to send it to port B, R17, and then out TIFR R21, clear ICF1, just jump L3, and that will be waiting over there. So that's all you need to do. If you have any question, note it down and you can ask me during the QA session. We'll carry on with the next section.